The launch of ChatGPT 3 years ago brought the concept of artificial intelligence into our daily conversation. Today, it seems like all industries, including lab medicine, are integrating AI with the promise of making our lives easier. How do we best navigate implementing this technology into the clinical microbiology lab? How will it be regulated? And what is AI exactly, anyways? Welcome to Editors in Conversation, a podcast brought to you by the Journal of Clinical Microbiology, available at asm.org/JCM. Editors in Conversation is supported by the American Society for Microbiology, which publishes JCM. I'm JCM Editor-in-Chief Romney Humphries, and I'm joined today by two colleagues and good friends, Dr. Susan Sharp and Dr. Kendall Bryant, who are going to talk to me, or at least educate me, all about artificial intelligence and how we might implement this in our clinical labs. So Dr. Sharp, welcome to Editors in Conversation.
Thanks, Romney. Appreciate being here with you and Kendall. Sounds like it's going to be fun.
Should be fun. I hope so. Hey, Dr. Bryant, welcome.
Thanks for talking to us about AI, something that I really like to talk about.
Yeah. And you're our resident expert. So it's very exciting. So maybe Susie, if we can start with you and maybe let's set the stage for our audience. So we're going to focus our conversation today on AI and how it applies to the microbiology lab and specifically to microbiology lab automation, something I think you're pretty familiar with, having spent several years working with Copan on this, right?
Yep.
And so for the listeners who are maybe not quite as, close to this as you are, could you tell us a little bit about microbiology lab automation and how AI is involved in that?
Yeah, sure. Bear with me. This might be just a little bit of a lengthy answer so that we can get everybody on the same page. Microbiology laboratory automation consists of using automated instrumentation to assist the laboratory in processing microbiology specimens, primarily that come in for culture. It includes upfront specimen processing instrumentation. These instruments will take the specimen, they'll mix it, they'll decap the container, they'll take an aliquot out of the container. They will then recap the specimen. They'll take that aliquot that they took out, they'll plant it, and then they'll streak it, and then they'll shuttle those plates off to the incubator. Now, microbiology laboratory automation also includes continuous incubation, or what we call smart incubation. Smart incubation means that the cultures are in the incubator all the time. It's not like out in the general laboratory or non-automated laboratory where people are getting in and out of the incubators all the time. So they're constantly disrupting the temperature and the atmosphere in there. With the continuous incubation in the smart incubators, the cultures are always being incubated. So it just makes sense that the organisms are going to grow faster when they're in those continuous incubation environment. And MLA, microbiology laboratory automation, or MLA, also includes the use of digital imaging. Digital images are detailed photographs that are taken of culture plates at user-defined times and are used then by the microbiologist. These images are used for review and interpretation of culture results. So these all together encompass what is known as microbiology laboratory automation. So we're also going to talk about AI. So artificial intelligence, or AI, are software programs or algorithms that are most generally used alongside of laboratory automation. These software programs consist of helping the microbiologist with culture interpretation. In doing that, it can sort cultures into like buckets or like folders. For example, all cultures that have a no growth can go in one folder. Cultures that have insignificant growth can go in another folder, mixed growth, etc. They can also do some quantitation of organisms on the plate for you. And they can even offer some preliminary identification of organisms as well as other functions. So really used together, automation and AI can significantly aid the laboratory with culture setup, incubation, also culture interpretation, and hopefully some gains in laboratory efficiencies. So if it's okay, Romney, I'd like to give just a couple examples of how AI is used in the microbiology laboratory. So let's talk urine cultures first. That's probably the one we think of primarily when we talk about algorithms and what people will bring on first for automation and algorithms, actually. So with urine cultures, there's been algorithms that have developed that can segregate or sort organisms or cultures into those with, like I said, no growth, those that have insignificant growth or less than 10 colonies on the plate, even contaminated growth. The algorithms are sophisticated enough to be able to look at the plate and say that there are three or more different colony morphologies on this plate. They all look like different organisms, so this is a contaminated culture. Again, they can quantitate at less than 10 colonies, 10 to 50 colonies, 50 to 100, greater than 100 colonies. And like I said, also give some preliminary IDs, specifically in this case, E. coli from a McConkey plate. So if you have a urine in the laboratory and it's plated to a blood in McConkey, the algorithm will see that it has growth on both plates, that it looks like there's 100 colonies on both plates, there's a single morphotype present, and the McConkey looks like it has an E. coli on it from what I've been trained, me being the algorithm. Looks like it has what should be an E. coli on it. So the algorithm could generate a preliminary report that says greater than 100 colony forming units per mil of E. coli, susceptibility testing pending. Algorithms also work quite well with our chromogenic auger, sorting what is a negative, doesn't have the right color, and separating those from the ones that have suspicious colonies or a color that could be the potential pathogen.
Yeah.
Now, depending on if the auger has any kind of an FDA clearance for identifying the organisms directly off the plate, then the algorithms can assist with that as well. They can assist with looking like at throat cultures. Does the plate have any beta hemolysis or no hemolysis, and separating those cultures out? So basically, it just gives you a good way of sorting and grouping together culture results so that they can be quickly reviewed and sent out or have further workup done.
Yeah, that's really cool. And it's kind of fun too, right? Like, I think, speaking of urines, we all have our favorite urologist who phones the lab to complain about, whatever. And is it powerful to be able to show that individual, hey, here's a picture of the plate. The lab's not lying. This is exactly what it is. And you can see it for yourself. So that's pretty cool.
And the last thing I'll bring up, one of the other things that AI can do is an auto release mechanism. Our colleagues in chemistry and hematology in the core laboratory have been using auto release of patient results directly from the instrument to the medical record for decades now.
Yeah.
Algorithms also exist to do that for microbiology. Currently, there's, I believe, only one FDA cleared to do that in the United States, but there'll be more of that coming.
Yeah. I mean, that's super powerful because it speeds things up so much by being able to have that result just flow straight through. Cool.
Exactly.
So that's that's really interesting. And you mentioned our colleagues in the core lab, right? So if I'm talking about AI, so is this essentially the same type of technology that they use, for example, in hematology with their automated differentials, or is this something even more sophisticated than that?
I mean, I sort of think it's something pretty close to that because it's sort of like putting cells into buckets.
Yeah.
And so this is sort of putting colony morphologies into buckets or looking at colonies on the plates and putting them into it. So I sort of think of AI as being one of those things that if you could come in and work your bench every day and all your plates were already sorted out for you. Like you already know these are all the no-grows. These are all the stuff that has something predominant on it, and these are all the ones that are maybe E. coli or stuff like that. How much easier would your day be knowing that you're pre-sorted everything? So that's sort of how I think currently what AI is doing. I think it probably will do much, much more in the future, though.
Yeah.
Yeah. If I can just chime in, Kendall, I agree. And it is kind of like what you stated, Romney. It is training, and as Kendall said, it's training an algorithm to accurately recognize something on an image, right?
Yeah.
But especially in microbiology, combinations of algorithms are oftentimes used to help interpretation of lab results. For example, I can get a couple examples. Say you have a young woman who comes into the clinic with a possible UTI. Urine's collected, sent for culture. Looks like it has 10 hemolytic colonies on a blood plate only, or less than 10 on a blood plate only, the algorithm would call that insignificant, right? Less than 10 colonies. But if the algorithm was trained to also use patient demographic information, it would see that this is a woman of childbearing age, and the algorithm would send that culture, even though it might be considered insignificant, it would send that culture to be reviewed. So those 10 colonies of non-hemolytic growth on the blood only could be ruled out, and to show that there is no group B strep there. Also, just in your example of urology, most of our urology cultures would be found out as contaminated. But again, if the algorithm was trained to look, at patient demographics, it could see, okay, this is a urology from such and such a clinic. We've already agreed that we would work up, their cultures. So the algorithm would automatically send that for workup. So basically you train them for what you want them to do. Then you just have to let them do what they do and let them work for you.
That's awesome. Yeah, very cool. Can they also answer the phone call when the urologist phones by chance, or no?
Yeah, somebody should work on that, right?
Yeah, I think so. I think that's the money. That's the money right there. So Kendall, you're actually in the process of doing this, right, in our lab at Vanderbilt, and so maybe you could tell us a little bit about why you're kind of pursuing the AI algorithms as part of our lab automation and what you're looking at first.
So one of the main reasons sort of goes back to what Susie was saying in the beginning about having more efficiency in the lab. Also, over time, we all know that we struggle with staffing at times in the lab. So making some of the easier things more efficient for the techs that we have that are working would be a great help for them. So I'm thinking that that's the main reason. And, there's so many things we do every day in the lab that take a lot of time, but really, maybe they shouldn't take a lot of time. You have to touch every plate to say that it's no growth, but maybe if the AI can sort all those out for you, that's a huge time saving. And we all know that a lot of cultures are becoming much, much more complex now because things are more resistant. You have to drop extra tests. So giving the technologist more time to work on the more complicated culture by making some of these more straightforward things a little bit easier. So the first thing that we're going to start with is probably some of our chromogenic screening augers, because those are probably the most straightforward for us. Mm-hmm. We have a ton of group A strep screens that we do every day, especially as we're going into respiratory season. So I think doing something like that where it's a chromogenic media, it's a pretty straightforward algorithm, is that the AI just has to say, is there colony growth on this plate, and is it the right color? And then it can call it positive. So those are sort of where we're starting out with, and then we're going to move over into our urine cultures. Mm-hmm. We do use chromogenic auger for our urine, so we're really hoping with the chromogenic auger that we're using that we'll be able to sort out, like, all of these are pure cultures of E. coli, these are pure cultures of other enterics, and then these are contaminated, and then some of them would be like, these are some of the group B streps and things like that. So it can sort of put everything into buckets for our technologists so that they just don't have to spend as much time going through every culture.
Yeah.
And then hopefully one day we'll actually get to the point where we can auto-release some of this stuff. But I don't think there is a lot of auto-release right now in the United States, at least.
Cool. But I have to say, so watching Dr. Bryant come into this lab, it's been kind of like a masterclass on how to set a lab up to get ready for this, right? So you mentioned bringing on the chromogenic auger for the urine cultures. I mean, that's something that you implemented with an eye towards this is the future. So, I mean, it's been really cool to watch.
It took a while for the plan to come together, but it all came together in the end. So.
Oh, man. Yeah. I mean, it just feels like it happened like that. But I mean, that's just my perspective. You did all the hard work. So, I mean, this sounds fabulous, right? So we're going to get this computer algorithm. It's going to read our cultures for us. It's going to sort things. I mean, it sounds like there's really no downside, but it can't possibly be this easy. So, Susie, from your perspective, what are the biggest challenges from the industry side in using AI algorithms in clinical microbiology?
Yeah, let me start out by saying just a couple of things about bringing in your automation for the first time, which oftentimes goes hand in hand with or comes first before your algorithms are in place. I think the number one thing that we need to convince laboratories to do, and I know Dr. Bryant was very good at doing this, is to convince a laboratory to bring on as much liquid-based microbiology collection devices as possible before they bring their automation into the laboratory. This is going to allow the most clinical specimens to be placed on the automated platform, and then you'll be able to get maximum utilization out of that platform. So that's the first thing. Second, and this is even more difficult, is try to convince labs in order to get the maximum efficiency out of their automation and their AI, they should move to as close as they can to a 24/7 operation. That really is going to allow them to maximize the money that they've spent on this rather large dollar instrumentation and AI that goes along with it. And then I guess the biggest challenge for us on the industry side is FDA clearance. Currently, there's very few algorithms that have FDA clearance. So most of them, and there's a lot more than them that are used in the United States. So they're being used as laboratory developed tests. And as we know, this is hard for some laboratories to bring in. They either feel like they don't have the expertise to bring in a lab developed test. Some laboratory administrators are very leery or adverse to bringing in non-FDA cleared tests. And from, again, the industry side, no laboratory seems to want the same workflow. So it's a lot of work on both sides, for the customer, the user, and for industry as well.
Yeah, totally. And I guess, something I learned just this week, Vanderbilt has an AI committee. And so you need to bring any AI application to them. And I can only imagine that type of thing is going to increase, because I think a lot of people maybe don't understand how the bias that might be involved, and like how you really do these validations. And I know institutions are really worried about this. So, yeah. So, I guess, Kendall, I've had the benefit of kind of watching this. And I wonder if maybe you could talk a little bit about the challenges from the lab side in using these AI algorithms. Like, what have you seen? I know that you've just done a ton of socializing this idea with the staff, but tell me about that.
Yeah, so we're sort of lucky that a lot of our staff are all about making their lives easier for some of this stuff. So, doing the urine bench can be quite challenging at times because it's just such a high volume bench. So whenever you tell them, well, maybe this can really help you out, so they're fairly excited about it. I think, of course, a few people are probably a little leery about the computers are taking over, but again, I think we all have to, say that it's going to help sort the plates for you, but a human is going to be making the decisions for most of this, at least for, I want to say, for the next 5 or 6 years, I would say, until the FDA decides how we're going to actually approve these algorithms. Mm-hmm. And so the biggest challenge right now, as we are just starting, so we've just started some of the paperwork and starting talking about how we want to sort our plates out and stuff, is actually making sure that your protocol in your own lab is that everybody understands the protocol the same way and everybody is actually reporting everything the same way. Because we don't want to have sort of some policy drift going on, and so all of a sudden you have a lot of outliers while you're trying to train your algorithm. So we put a lot of work into really streamlining our policies, making sure that they're very clear when this is, and then we've also been actually going back and auditing to make sure people are all reading it the same way, so we can fix anything in the policy now before we start training the algorithm. So that's been a little bit of work, and actually seeing that sometimes what we think is very clear whenever we write the policy, some people interpret it just a little bit differently. Yeah. But you always want your algorithm to interpret it the same way. So you don't want a lot of outliers in your set that you're using to train your AI.
Yeah. Well, and I guess in my mind too, maybe this hurdle is a little bit easier to overcome with the fact that we've all kind of implemented MALDI-TOF mass spec. I feel like, that transition in the micro lab towards more automation is kind of already on its way.
Yeah, and I'm sort of hoping, we don't have some of the issues with the MALDI-TOF where people blindly trust. Sometimes they blindly trust what the ID is on a MALDI-TOF. So I think that's the other thing we're going to have to balance is how much do we need to check in on these algorithms and how often do we have to do another validation set to show that it is still working the way that we thought it was working and things like that. I think there's just a lot of those questions that we still have to ask and get an answer.
Maybe make sure that the AI is not coming up with delusional bacteria like it does with. Okay, so we've talked about standardization, right? And that's so important within the lab. But the other thing, Susie, you mentioned that I wanted to touch on is how customized this all winds up being, right? Because every lab does something kind of differently. I mean, it's kind of like the beauty of microbiology, but probably also the frustrating part. So how are companies, from your experience, and regulators approaching this, knowing that this can be so customized?
Yeah, just to step back a little here, if I might. Before you even get to where you're at the stage of developing an algorithm, there's a lot of decisions that have to be made. For example, you have to decide what lighting you're going to be using on the culture plate when the image is taken. You have to decide on your incubation time, what media you're going to use, what manufacturer of media you're going to use, what streaking pattern you're going to use, and a variety of other decisions have to be made. And those all have to be decided prior to starting any algorithm development. And as Kendall said, also, everybody has to be reading the cultures the same way all the time. So you have to get that done in the laboratory as well. So developing an AI algorithm, it's a lengthy process for both the laboratory and the manufacturer. And Kendall talked about building the algorithm. And if I can, just take a minute here to kind of explain how that works.
Yeah, please do, because I think it's a mystery.
Yeah. To develop an AI algorithm in microbiology, it takes hundreds, or you ask Kendall, probably thousands of curated images that the manufacturer needs from the laboratory. And a curated image is basically a culture result that has been read by experts, maybe several experts, and they all agree on the results. So we know that curated image has a result of truth, right? So every time you run these curated images through a developed algorithm, you compare those results to the results of the truth. So you can see how accurate the algorithm is. So say it has a 93% sensitivity or agreement. You're going, okay, that's not good enough. We want it higher than that. So you tweak the algorithm a little bit more. You see where it made the mistake. So you tweak it so it won't make those mistakes again. And then you run those curated images through it again. And you continue that process of running curated images and tweaking, and running the images and tweaking, and running the images and tweaking, until it gets to where it has an acceptable result according to the user. And then you put it out in the test environment, because you want to see how that algorithm works in the real environment. So you send through a smaller number of curated images, but images that the algorithm has never seen before. So you can see how it works in a real life environment. If it works as well as expected, great. If it doesn't, it goes back to the training mode and you go through those steps all over again. So once the algorithm is accepted, it's locked down, it's considered validated. And this, again, the process can take several months. And one note I want to make, and go back to the first thing I said here, was that one thing that's kind of hard sometimes to get across to laboratories is that once an algorithm is locked down, you can't make any changes to it. I told you all those decisions that have to be made up front. That's why those are so important. Because if you say, okay, I did my urines at 18 hours, I think I can really read those at 16 or 14. So let's change it. You can't read 14-hour images using an 18-hour algorithm. So it's important to make sure you understand where it is you want to go, where you want to be after you develop this algorithm, and make sure all those decisions are made upfront and are correct for where you want to go.
Yeah. This brought up a question for me, and Kendall, maybe you can chime in on this one too. So I've worked in 2 labs now, and to me, E. coli grown in my lab at UCLA looks a lot like E. coli grown in my lab here at Vanderbilt. So are there, does this training model all happen in the lab where the testing is going to be performed, or is there like crowdsourcing of images that can happen?
So I think that sort of hits on like the holy grail that we're looking for is like an annotated set of images that
Yeah.
every lab can use, but then we can just report them the way that we report them in our lab. So that way we don't have to wait for hundreds and hundreds of patient pictures to actually go through to be curated. So I think that's one of the things. But I think another thing that we really need to work on as a microbiology community is sort of having some standard ground rules for how we work up all of our cultures. Which
I laugh
maybe
because I know. Yeah.
So I think, like if we could come up with, these are pretty much the foundational ways we want a urine culture to be worked up, then a company can actually say, well, here is the algorithm out of the box. And you can imagine how much more efficiency you get if we could have went live with the AI algorithm the same day we went live with our automation system, right? Yeah. But instead you have like it could be a lengthy lag, probably at least a year, maybe 2 years before your algorithms, because you sort of got to get used to automation first. And then after you get used to the automation, then you can start doing the pictures. So, I think that's sort of what's lacking, is a little bit of standardization.
Yeah.
We can't, and then everybody would have to agree in your automation system. Are we going to read our urines at 16 hours, 14 hours, 18 hours, 24 hours?
Good luck with that.
And again, good luck with that.
I was just going to ask, okay, let's be honest. How realistic is this? I think when we were doing respiratory work back in my previous life, we pulled 200 labs and there were 200 different ways to do a respiratory culture at the end of the day. So, yeah.
Yeah. But I mean, going back to why we can do like the cell sorting, like the Cellivision in Core Lab, it's because everybody did agree this is this type of cell and this is what it looks like, right? Yeah. And so you can start those on day one, unlike us, where we like a little bit more of the gray, or a bit more of the gray, I guess I should say.
No, it's because microbiology is more complicated than hematology. Yeah. I just say that because my boss is a hematopathologist and I like to egg him on. And I guess it would have to be customized to your patient population, right? So if you're at a children's hospital, maybe things are a bit different than an adult or transplant versus community.
Yeah. I mean, I think that's one of the reasons we have all the different protocols that we currently have. And that's why we have very few cleared that are used FDA protocols, because everybody's protocols and workflow doesn't fit into one nice, little bucket. There will be more algorithms coming, FDA cleared algorithms coming in the future. And I think the lack of standardization is an issue, but I think some companies are starting to look at considering templates, if you will, to help streamline the process. So it starts with a preset workflow, and then the users can make some modifications, probably minor modifications to that workflow, but it would still allow a more streamlined approach by still allowing some individualization of the workflow.
Yeah.
And so how do you think the regulatory part of that would be? Because everything's customized, so what do you think the FDA will eventually allow to be automatically released if everybody's doing it differently? Well, how does a company even go to the FDA and say, we have this great algorithm, but everybody's doing it a little
adventure.
Yeah.
I think the answer is, and I think some companies are approaching this with the FDA, and Romney, you'll know this term better than I do, and I'm going to get the letters wrong. Is it CCPP or whatever those initials are with the FDA that allows a company to submit something, and with the understanding that they will be making small tweaks to it in the future going forward, and the FDA will agree if those tweaks and those modifications are small enough that it will not take a robust application, and that it could go much faster. So I think that's the way that some companies are going to approach this, by approaching it that way upfront with the FDA with a few algorithms, and then being able to make those tweaks. Okay, we're going from 16 to 14 hours, or we're going from this chromogra to that chromogra, but it's the same color pattern, or whatever the case may be.
Yeah. I think they're pre-approved change control plans. So essentially you tell FDA, this is how we're going to do our changes. This is what we'll do to validate them. Do you agree or disagree? And if they agree, then it's just like a note to file rather than a whole new submission. Yeah. And I mean, this is nothing in medicine is static, right? And I think that the FDA is becoming more and more aware of this. I mean, I think a lot about these big, giant cancer next generation sequencing panels that are constantly being updated, right? And so I think it's just the reality of medicine, things are evolving so quickly. Yeah. So Kendall, tell me, okay, in the real world, what's it like? I mean, how has this changed things? What have you been like, oh man, I wish I had known this before we did it? And you've done this twice now with the automation, but yeah, tell me about that.
Well, you should be lucky. I think I made most of my mistakes at my first job. Or I learned a lot from my first job. So, I think really, if you're going to do AI and you're going to bring in automation, I think you really just have to have a plan of not let's get it in and let's get it going. Let's think about all the uses we want for this for the next 5 to 10 years and really start planning ahead of time, because there's so much work you can do before you even get your capital in for your instrument. Like you said, I changed over to our chromogenic auger for our urines because I knew I wanted to use an AI algorithm to sort them. And so we changed to our chromogenic media probably about 2.5 years ago. And so we still don't have the algorithm yet, but all of our staff are used to using that. Whenever Copan did our time, like we know we validated our system with that auger, so we know all the incubation times that we wanted to use. Copan also knows the color palette and the lighting conditions and everything for that media for us. So it's a little less work on their end if we decide, oh, now we're going to do AI, let's change media and try to start an algorithm. So I think really thinking about long-term what your goals are is very helpful.
Mm-hmm, mm-hmm. Yeah, totally. Susie, any thoughts from you? I mean, you've seen this implemented in so many labs at this point. Like, what's it really like?
Yeah, for the laboratories that really take this home and really drive it through, they're being thrilled with the results that they're seeing.
Yeah.
But primarily the decrease in turnaround time, not only the decrease in the turnaround times, but and especially the decrease in turnaround times when they're doing auto release. There's people in Canada doing that, and they're seeing decreasing turnaround times by not 2, 3, 4, 6 hours, but 24, 28, 32 hours. So it can make some big difference in turnaround times out there. And we've had laboratories in the United States even comment that, we are ready to go with some auto release functions because we know that the automation is doing as good a job or better than what our technologists can do.
Yeah.
Just because it has eyes that magnify things 1,000 times more than we can, and et cetera. So yeah, I think once you really grab onto it, I think it's a good thing for laboratories, and it's going to help. We know we have positions out there we can't fill, and I kind of see automation and AI filling those positions, not replacing anybody, but helping fill those voids that we're having in the laboratory.
Yeah, I mean, and just to that point, as an anecdote, our lab, I think, had some apprehension, as people do, with change. And a couple of months ago, we were really struggling from a staffing perspective. We had a couple of people retire and some departures and some medical leave. And one of the technologists, who was kind of one of the ones that was the crankiest about doing this, said, Dr. Humphries, I don't know what we would have done if we hadn't implemented this. I mean, it makes our lives so much more efficient. So that was cool to hear. Yeah. All right. Well, so as we wrap up, what's the future, right? Are these plates going to, be able to be imaged and identified and signed out and nobody ever needs to look at a culture, or where are we heading, guys?
I think maybe in 10 years, we might get to some of that. I think there's also some really cool papers out there right now, too, looking at the image can actually ID the organisms on the plate, so regular blood plate. So eventually, maybe we'll be able to hover over a colony on a plate and we sort of get to know what it is instead of having to do a MALDI. So I think that's probably the far future. In the near term, I really think a lot of labs will start really implementing these algorithms to get their cultures out quicker. And I think we'll see a lot of efficiencies and probably a lot of quality. The quality will probably be the same across your lab once you implement a lot of these algorithms, because you are calling a contaminated urine the same every time. You are doing this more streamlined way of doing it. So,
yeah. Susie, what's the world of possibility in your mind?
Well, I agree with Kendall. I think that the next 10 to 15 years is going to bring some major changes in decision making and algorithm development, all the way from when the culture is first planted and goes on the instrument to AI looking at it and deciding whether it needs to be worked up or not. To that end, I think algorithms are going to continue to evolve to meet the needs of the laboratory and address some of the gaps that we see in the culture laboratory. For example, there's already software out there that will automatically pick colonies from plates to be used for identification and susceptibility testing. The staff doesn't have to tell the algorithm what to do. It can pick them themselves and then send it to an instrumentation that will read those coordinates, pick those colonies, put them on your MALDI-TOF plate, and make your susceptibility suspension. So, those already exist. So that's where we're going, and we're going to do more. I think as we incorporate more and more patient demographic information into our culture reading, to let us know that there's specialized testing that needs to be done on this patient, we'll have more, if you will, individualized medicine in the culture laboratory. Yeah. So there's lots of data, a lot of publications out there that shows how well this works, how it can increase efficiencies in the laboratory. It'll continue, I think, to support our technologists going forward in their daily work, allow them to really spend their time working on the complicated cultures and not worried about all these no-growth cultures. And I don't think AI, at least in the next foreseeable future, is going to replace our technologists. I think it's going to, as I said, mitigate some of the shortages that we have out there, increase the accuracy of our results, which is always a good thing, decrease our reporting time, which also can hopefully be very beneficial to our patients. And I think, we've got some very talented programmers out there that really do understand clinical microbiology that are developing these algorithms. So I think they'll continue to find ways to aid microbiologists in the culture lab, and allow for even more efficient review and resulting of our results.
Yeah, I agree. I think it's really exciting and really, really cool to see. So thank you guys both for joining me today and chat a little bit about this field. It's fascinating and it's really exciting to see where it's going. So Kendall, Susie, thank you so much.
Thanks.
Thank you.
Awesome. If you've enjoyed this, please subscribe to the podcast and share with your friends and colleagues and neighbors. We'll link some papers on artificial intelligence in the microbiology lab along with this episode. You can find those in the show notes or the section below if you're watching on YouTube. And Editors in Conversation is supported by the American Society for Microbiology, which publishes JCM. If you're an ASM member, you get 50% off your publication fees when you publish with JCM or in any of the other ASM journals. Thanks again for listening to Editors in Conversation, and goodbye.